Hi, I'm Dan Bauer and welcome to CBA Office Hours, where Patrick Kern and I talk about different quantitative methods and how they're applied in behavioral health and social sciences. Today I'm going to extend our series on the linear regression model. In prior episodes we've talked about what is the linear regression model, how is it estimated, how do we make inferences from the model, how can we include multiple predictors in our model. And in all of those episodes, we've assumed that the predictor is continuous. So we've had a continuous outcome and we've had a continuous predictor or multiple continuous predictors. But sometimes our predictors aren't continuous. Sometimes our predictors are categorical. So we might want to include a predictor like the sex of the participant, so male versus female. Well, that's a categorical variable, and including that in the regression model requires that we understand how categorical variables can be incorporated into the model. So that's what our focus is going to be today, is how do we bring categorical predictors into our regression model. And this is actually one of my favorite topics to teach about the regression model because it provides an opportunity to think about how the regression model is really a very general framework that encompasses some of the procedures we've already learned about in our intro stats, but think about them from more of a model-based approach so that we can think about alternative models that we could potentially apply to our data as opposed to sort of taking a recipe book formulation of saying, oh, well, if you have two groups and you have a continuous outcome, then you must do a two-sample t-test. All right, so we're going to be less focused on a particular procedure, whether it's a one-sample t-test or two-sample t-test or a one-way ANOVA, and we're going to move that into a model-based framework and think about how we can specify models and include categorical predictors. So I'm going to start out by just thinking about the one-sample t-test, the humble one-sample t-test, the very first inferential procedure that anybody learns about an intro stat, at least typically. In the one-sample t-test, what do? Is we observe a sample mean, right, M, and we want to make some inference about the population mean mu, right? And so we take that sample mean and we have some null hypothesis for what that population mean might be. So our null hypothesis might be that that mean is 0 in the population. All right, and our one-sample t-test, what we do is we take our sample statistic M and we subtract that null hypothesized value and we divide by the standard error of the mean, and we get a critical, or not a critical, but just a t statistic, we'll call that t star, and that is distributed as a t with n minus 1 degrees of freedom. And when we learn about the one-sample t-test, we learn about this computational formula, right? We look up this t-value on the t-distribution, we find the p-value associated with that. If p is less than 0.05, we reject the null hypothesis. Otherwise, we can't reject the null hypothesis, right? That's how we learn about this, this procedure to begin with. And oftentimes, because the null hypothesis tends to be 0, we might just leave that part out of the formula, right? Implicitly, it just kind of goes away. Now, let's think about that from a regression standpoint. All right, so that's sort of a procedural way of thinking about the one-sample t-test, but we can also think about this from a regression-based approach, right? So in our regression model, we're going to have an outcome variable, and we'll designate that y as we have before. And then to mimic a one-sample t-test, we have a model that has no predictors, just an intercept, all right? Well, in our regression model, right, what is the expected value of y? Well, that's then just beta naught, right? And that is equivalent to our population mean, right? So there's the expected value is just the average if there are no predictors, right? Our best guess is the average in the absence of any other information. So in our regression model, we could stipulate a regression model where we have only an intercept parameter, beta naught, and then we would get in our regression model a test, right? We would get an estimate B0, and we would get a standard error for B0, and that would be a t statistic, all right? And if you remember from prior episodes, that's distributed as a t with n minus p degrees of freedom, where p is the number of parameters, but notice in this case, that's going to be n minus 1, and we're going to get exactly the same t-test from our intercept-only regression model as we would if we did a one-sample t-test in the classical way. All right, so that's the one-sample t-test. Now, let's extend to the two-sample t-test, where we actually do have a categorical predictor. All right, so in the two-sample t-test, the way we traditionally learn this is we get our mean for group 1, M1, and we get our mean for group 2, M2, right? And we're going to have some null hypothesis about how these population means are different from one another, and we want to evaluate that null hypothesis with these sample means. So typically, our null hypothesis is going to be that the mean for group 1 is equal to the mean for group 2, or equivalently, the mean difference is 0. All right, so to get our t-test, we take M2 minus M1, and we divide by the standard error of that mean difference, and that gives us a t-statistic that's distributed with n minus 2 degrees of freedom. All right, we lose an extra degree of freedom because we had to estimate 2 sample means instead of just 1. All right, so that's our 2-sample t-test, and again we have a null hypothesis here of 0, so we have M2 minus M1 is 0 divided by that standard deviation, and we get that t critical value, our t statistic. We look that up, we compare it to the critical value, we see whether p is less than 0.05. If p is less than 0.05, we reject our null hypothesis that the two groups are equal, and if p is not less than 0.05, then we do not reject. All right, so now let's put this into our regression-based framework. So that's the 2-sample t-test as we know it. Now let's do it as a regression model. So in our regression model, what we're going to do is, again, we're going to start out with our outcome variable, y. Right? So we have some outcome variable. Let's say we're interested in evaluating whether or not there's a sex difference in antisocial behavior for adolescents. So our male adolescents, do they exhibit higher average levels of antisocial behavior than female adolescents? Well, we could just do that 2-sample t-test that we just saw, but we could also do this as a regression model. So in the regression model, what we're going to do is we're going to have our outcome variables. So y here is going to be antisocial behavior, and y is going to be predicted by the group membership of the individual. Now the way I'm going to write this regression model, oops, I may not do b, but do beta, is we're going to have an intercept, and now we're going to have a slope associated with the sex of the adolescent. And the way I'm going to do this is I'm going to set this variable male. Male is going to be equal to 0 if the participant is female. And male is going to be set equal to 1 if the participant is male. All right? So in my data set, I have coded this variable male to be 0 for females and 1 for males. Now when you do that, a lot of times this will be referred to as an indicator variable, right? So an indicator variable is a variable that takes on a 1 for one group and a 0 for the other, so it indicates what category the individual is in. It's often nice to name your indicator by the category that's indicated as 1. So here my indicator variable is called male because 1 indicates male. If I instead wanted 1 to be female, then I could call my indicator variable female, and I would just switch these 0s and 1s around. Right? And it's equivalent either way. You're just kind of flipping the direction that you're looking at, but you get the same kinds of results. All right, so that's how I'm going to code this. All right, so now let's think about this. What this is doing graphically, right, is, you know, in all of our prior models, we've had continuous predictors. Right? And so when we plot y against x, I'm not going to draw it out, but we would get a scatter plot with a cloud of points. Well, what we're going to get here is our x variable is male, right? So we're going to have two possible values, a 0 and a 1, right? And we have a scatter of dots at 0 for the girls, and we have a scatter of dots at 1 for the boys. Right? And right here is the mean of girls, and right here is the mean of boys, and we're interested in that mean difference, right? Well, remember what your regression slope is it's the change in y you expect to observe for a 1-unit change in x, right? So a 1-unit change in male means going from female to male, right? So we've got a slope of a line right here, and that slope represents beta 1, right? So that difference between the two means is beta 1. So beta 1 is capturing the mean difference between these two groups. So when we get our estimate of B1 and we put it over the standard error of B1 and we obtain our t-statistic, which is distributed as a t within minus p degrees of freedom, p being 2 now, right? We're going to get an exactly equivalent t-statistic to what we would get in a two-sample t-test, right? And another way of seeing this is through the model equations. As we can say, what is our expected value for y if male is 0, right? So for a girl, the expected value is just going to be beta naught. So we're going to have beta naught plus beta 1 times 0, right? Whereas for a boy, right now male is 1, and we're going to get beta naught plus beta 1. Well, right? So this is our mu1, right? So that's our mean for girls, and here's our mu2, that's our mean for boys. And so our mean difference, mu2 minus mu1, is just equal to beta 1. It's the difference between these two, right? So beta naught cancels out. We're left with beta 1. We test beta 1, right? We get our estimate of B1 over the standard error of B1, and that's equivalent to our t-test of the mean difference, right? The other thing we can see with this equation is how do we interpret beta naught? So we focused on beta 1. Beta 1 gives us a parameter that's equal to a mean difference between the two groups, and getting an estimate for that and a standard error for that enables us to obtain a significance test and inference on whether those two groups differ in their means. But how do we interpret beta naught? Well, beta naught is just the mean of whatever group has been coded 0, right? So in this case, it's the mean for girls. So we're going to get two parameters out of our regression model. We're going to get a B0, and that's going to be our estimated mean for girls. And we're going to get a B1, and that's going to be our mean difference, right, between boys and girls. All right, so those are our two parameters in our regression model. So that's our two-sample t-test. And the way we've coded this categorical predictor with an indicator variable, sometimes it's called reference cell coding, sometimes it's called dummy variable coding. It's just a way to bring this predictor into the regression model to obtain estimates that enable us to observe the effect of categorical predictors. All right, now what we're going to think about is, all right, well, that was easy enough when we only had two categories. But what if we have a predictor with 3 or more categories? Then what do we do? Well, in the classical statistics approach, right, what you would do is a one-way ANOVA model. So here we'll see how we can do the equivalent to a one-way ANOVA model, but using the regression model. All right, so let's think of a different example. Instead of antisocial behavior, we're going to look at depression. Let's not look at depression. Let's look at marital satisfaction for couples who are assigned to some kind of couples therapy condition. So they're either in a control group where they don't get any couples therapy, or they get cognitive behavioral therapy, we'll call that CBT, or they get insight-oriented psychotherapy, so more like psychodynamic type stuff. So those will be our three conditions that we're interested in, and we want to know, is there an overall effect of conditions? So we've got these three levels to the condition variable. We've got control, and we've got psychodynamic, and insight-oriented, and we've got CBT. So control, CBT, and insight, right, are the three levels of our categorical predictor that we're interested in. All right, so what we're going to do is we're just going to extend what we saw with the two-group case. So in the two-group case, we had male, female, and we created one indicator variable that differentiated these two groups. For any categorical predictor, right, so any categorical predictor with C categories, we're going to need C minus 1 indicator variables to differentiate them, right? Because if I know you're not in CBT and I know you're not in insight, then you have to be in control. So you know C minus 1 of these grouping possibilities, then of course you know what the last one's going to be. And so we're always going to have C minus 1 coding variables, and there are different ways of creating coding variables. We're going to again focus on dummy variable coding or reference cell coding. And so what we're going to do here is when we have 3 levels to our categorical predictor, we're going to create 2 coding variables. All right, so we're going to have C1 and we're going to have C2. All right, so C1, actually let me bring this down just a little bit so it's easier to look at. So we've got control, we've got CBT, we've got insight, we've got C1 and C2 are the 2 coding variables we're going to create. And I'm going to make my control group the reference group. So I want to observe effects relative to the control group, so I'm going to make that the reference group. So I'm going to code that 0 for each of these coding variables. And then if the individual is in CBT, I'm going to give them a 1 here and a 0 there. And if they're in insight, I'm going to give them a 0 here and a 1 there. So what we've really done is just created 2 indicator variables, right? We have an indicator variable that we can call CBT, and we have another indicator variable that we can call insight, right? So we have 2 indicator variables, and these 2 indicator variables are going to differentiate the 3 categories of treatment. All right, so now we can build our regression model. We've got marital satisfaction is equal to an intercept plus a slope for CBT plus a slope for insight plus, of course, our usual residual. All right, so that's going to be our regression model. Now, in terms of interpreting the parameters of the regression model, it's going to be very similar to what we saw in that 2-group case. Now we have 3 possible outcomes, right? So we have an expected value for marital satisfaction if you're in control, right? And if you're in the control group, then CBT is 0 and insight is 0, and all that's left is beta naught, right? So beta naught is going to represent the expected value for the control group, or the average value for the control group. Now, what if the individual is in CBT, right? Now we have beta naught, but CBT is coded 1, so we add beta 1. Insight is coded 0, right? And so we don't add beta 2. What if you're in the insight group? Now we have beta naught plus beta 2. Beta naught, beta 1 times 0, beta 2 times 1. So we bring that beta 2 in. All right, so interpreting our parameters, beta naught is the average for the control group. Beta 1 is the mean difference between CBT and control, right? How much do you have to add to beta naught to get to CBT? And beta 2 is the difference between insight and control. Right, now, what's a little bit different here is that if we want to know what is the overall effective treatment group, we don't want to test beta 1 and beta 2 individually, we want to test them together. So we want to test both of those to see whether there are any mean differences at all between our 3 groups. So that would be equivalent to our main effect in a one-way ANOVA model. It's a multi-degree of freedom test because we have 2 parameters involved in that test. So let me make a little space here. Is in our one-way ANOVA model, the way we would write this is our null hypothesis would be mu control is equal to mu CBT is equal to mu insight. All right, so all means are equal would be our null hypothesis, and we would get our F test looking at sums of squares between and sums of squares within and converting those to mean squares and getting an F ratio and all the rest of it. But what we're going to do here instead is we're going to recast that null hypothesis in terms of our regression model. In our regression model, if those 3 means are equal, then that's equivalent to saying beta 1 and beta 2 are simultaneously 0. Right? So it's a joint test of those 2 parameters. If those are simultaneously 0, then what happens? this beta 1 and that beta 2 goes away, and the mean of all three groups is beta naught. All right, so there's no mean difference between the three groups. All right, so we're going to do a test, a joint test of those two parameters in our model, not just one parameter, but both parameters simultaneously. All right, and when we do that, we're going to get there. I'm not going to go into the details of where that comes from, but we're going to get an F statistic, and that's going to be distributed with an F distribution with the number of parameters as the numerator degrees of freedom, and then the n minus p as the denominator degrees of freedom. So we'll get an F statistic just like in the one-way ANOVA model, where we can see, well, you know, do these two extra parameters in our model, beta 1 and beta 2, do they offer an improvement in the fit of the model to the data versus only having a beta naught and assuming all three means are equal? And that F statistic is going to be equivalent to what you would get from a one-way ANOVA model, but now it's in a regression model. Now, usually, once we obtain an overall significant main effect in a ANOVA model, we're interested in where are the differences. And one of the nice things about the regression model is that we will automatically, we can get this F test, but we will automatically also get B0, B1, and B2 and tests on those. And so we can see, okay, well, here's the mean of here's our estimated mean for the control group, and here's our estimated mean difference for CBT. So did CBT result in a significant improvement in marital satisfaction relative to control? And then we'll also get B2, and we can see, does insight-oriented psychotherapy result in a significant increase in marital satisfaction relative to control, right? So it's always relative to that reference group. Now, we wanted to say, well, is CBT different from insight? Right, we could also get that test either by simply permuting our reference coding instead of making the control group the 0 category, making CBT or insight the 0 category, or by doing a simple linear contrast that most software programs will do pretty easily. And so we can obtain that test as well. But what's nice about the regression model is we automatically get these kind of simple pairwise comparisons relative to that reference group. So for instance, we might find that CBT leads to a significant increase in marital satisfaction, that B1 is significant, but that insight-oriented psychotherapy does not. And so it's not significantly better than no psychotherapy at all. All right. So that's our one-way ANOVA model recast as a regression model. So we can do this within the regression framework. And what's nice about that is it means that we aren't exclusively stuck with categorical predictors. We can use any mix of continuous and categorical predictors that we might be interested in. So let's consider a slightly more elaborate model. So we've got marital satisfaction as our outcome still. We've got our indicator variables, CBT and insight. But I also want to control for baseline marital satisfaction. Some of the couples that came into my study were already somewhat troubled before we even began the study, and other couples were less so, right? And so I want to control for that. So I'm going to put in beta 3 baseline satisfaction, right? Now that is a continuous variable. So now I've got a mix of a categorical variable represented through these two coding variables and also a continuous variable in my regression model. Now this model, right, so we've talked about the one sample t-test, the two sample t-test, the one-way ANOVA model. This model is equivalent to an analysis of covariance, right? So in an analysis of covariance, we have a continuous covariate that we control for, and we want to look for mean differences that exist between our groups after controlling for, holding constant, removing any noise associated with that covariate, right? And so in the analysis of covariance model, there's an assumption referred to as the parallel regression lines assumption, or the homogeneity of a regression assumption. And we're going to see that here, is that now what we've got is that we want to know what's the expected value for CBT, what's the expected value for insight, and so on. We can say, what's the expected value if you're in the control group, right? And I'm going to set baseline to some constant, right? So I want to hold constant baseline satisfaction. All right, well, that's going to be B0, sorry, not a very good beta. It's going to be beta 0 plus beta 3 times C, all right? And then I might want to know, what about if you're in the CBT group? Again, I'm going to set baseline to that same constant, beta naught plus beta 1 plus beta 3c. What if you're in the insight? Again, I'll hold baseline satisfaction constant. Now I get beta naught plus beta 2 plus 3 beta 3s. And you notice that if we want to see, well, what does beta 1 represent? Beta 1 is the difference in the means between control and CBT holding constant our covariate, right? So holding that constant at C, we isolate beta 1 by differencing these two equations. And likewise, if we want to know the difference between control and insight, right? Again, we can subtract and we can cancel those out, and beta 2 is the mean difference between insight-oriented psychotherapy and control, holding constant baseline satisfaction. All right, so we can control for some continuous variables while evaluating the effects of categorical variables. And vice versa, we can get the effect of baseline satisfaction controlling for treatment group and so on. Now, the assumption of parallel regression lines comes in through the fact that we only have one beta 3, right? Beta 3 represents the effect of baseline satisfaction on later marital satisfaction following treatment, right? And we're assuming that there's just one effect, just beta 3. That's all there is, right? So we can say, all right, well, what if we plotted out the relationship between satisfaction and our predictors? All right, so we've got our y variable, post-test satisfaction, and we've got our x variable, and I'm going to use the baseline measure here, that's the continuous one, and then we've got our grouping variable. All right, well, for the control group, CBT and insight are 0, right? So we're going to get beta naught, right, where x is 0 at no satisfaction. And then we're going to see that as satisfaction goes up, we may see that the later marital satisfaction goes up as well, right? And that's our beta 3, is that slope, is what's the effect of baseline satisfaction on later satisfaction, right? Now, within the control group, we start at beta 0, and we add to that beta 3 units per baseline unit of satisfaction. All right, well, what about the CBT group? In the CBT group, we don't start at beta naught. We go beta naught plus beta 1. All right, so we're going to go up beta 1 units. And now we have a regression line for the CBT group. All right, and the difference here is that beta 1. All right, so we get beta naught plus beta 1, and then we have the beta 3 baseline satisfaction. What about the insight-oriented group? Again, we're going to shift off of beta naught, maybe just to make things easier to draw. I'm going to assume insight-oriented is actually worse, and so the satisfaction is even lower, right? So we get a difference downward, that is the beta 2, right? But we get the exact same slope for the regression line. So all three of these regression lines have that same beta 3 slope. Sorry, it's getting a little sloppy looking, but hopefully you get the idea, is we have one slope, right? But we, in a sense, have three intercepts. We have an intercept for the control group, beta naught. We have an intercept for the CBT group, beta naught plus beta 1. And we have an intercept for the insight group, beta naught plus beta 2. All right, so we have three different intercepts to adjust the levels of these regression lines, but we have just one slope, beta 3, to indicate how baseline satisfaction is related to later satisfaction, right? So we can think of that beta 3 as the slope for this group. So we've got a slope for control, we've got a slope for CBT, we've got a slope for insight, and those slopes are all exactly the same beta 3. But we get mean differences through the coding variable, right? So the difference between these two lines is beta 1, the difference between those two lines is beta 2. Now, what analysis of covariance is doing, or this regression model, is saying hold constant x wherever you want, and we can see the mean differences among these three groups. Right? So we could hold x constant here, right? And we'd see those mean differences. We could hold x constant there, and we would see the same mean differences. The lines have the same vertical distance no matter where we go on the x-axis. All right. Well, what if that's not true? All right. What if the homogeneity regression assumption is not right? What if parallel regression lines don't hold? What if people who have worse marital satisfaction actually benefit the most from CBT and benefit the least from insight-oriented? Right? Then we have to talk about interactions, which is something we'll get into in some later episodes, hopefully. But right now, we're just going to assume simple main effects, that there's no interactions involved in the model. All right. So that enables us to have a mixture of categorical predictors and continuous predictors. Now you might be saying, well, couldn't we have multiple categorical predictors? Sure, and then you're going to get into things that look like factorial ANOVA, and you can get tests of the main effects of each categorical predictor as well as the interaction between categorical predictors if you believe that interaction to be there. And again, we'll kind of put off interactions to another day. But what's nice is that we can have this mixture of different kinds of predictors that we bring into our model. So we could put in baseline satisfaction. We could extend our model even further. We could say, well, let's also include some measure of stress. Let's also include some measure of, is there an infant in the home, right? Anyone who's had a child knows that's pretty stressful, right? So that can impact marital status. So we could include a lot of different things in our model, some of which are continuous, some of which are categorical. So treatment group is captured by these two indicator variables. It's a categorical predictor. Baseline satisfaction, continuous. Stress, continuous. Infant in the home or not, two possible values, 0 or 1. Indicator variable, categorical predictor. All right, so we can have this mix of different kinds of predictors in our model and get good estimates to interpret mean differences for one predictor holding constant other predictors. So we have a lot of flexibility in these models to incorporate the kinds of effects that we might be interested in. Now, what I have illustrated here is, again, it's reference group coding, dummy variable coding, use of indicator variables. That's not the only way to include categorical predictors in your regression model. There are other kinds of coding systems that can be used. So effect coding is another way of doing things, and there's unweighted effect coding and weighted effect coding. You can also do contrast coding. Contrast coding would enable you to answer questions that are a little bit different. So here we're asking the question, is CBT better than control? That's beta 1. Is insight oriented better than control? That's beta 2. But what if we wanted to ask the question, is treatment at all better than no treatment, right? So we want to say, well, CBT and insight together versus control, that's what contrast coding is really useful for. And we can create contrast codes that allow us to see, first, is treatment better than no treatment? And then second, is there any difference between the two treatments, CBT and insight-oriented? So there's a lot of different coding systems you can use to answer different kinds of hypotheses. But by far and away, the most common coding system that's used in regression models is this kind of indicator variable coding. It's straightforward, it's easy to interpret. Your regression parameters represent mean differences. You can get multi-degree of freedom tests for categorical predictors that involve more than 2 categories. You can include interactions if you want to. You can include both categorical and continuous predictors, so you have a lot of flexibility. Those other coding systems are kind of fun to play around with and explore and think about different ways of packaging information about mean differences between groups. But again, this is pretty much the most common way that people include these predictors in the model. So I hope that was helpful to see how we can include these categorical predictors in the model. And what we'll do in future episodes is we'll extend the regression model again further to look at interactions. So that's something that we haven't considered yet. But what if we have situations where the effects of some predictors depend on the values of the other predictors? So we can't just hold those values constant at any old place. It matters where. The effects differ depending on the values of the other predictors. Thanks very much for your time, and I'll see you next episode.